I borrowed code from this person here. This person wrote some very simple, straightforward VM detection routines, so they're not doing any kind of like advanced processor inspection or anything like that to try and figure it out. They're doing a handful of really simple heuristics to try and identify whether the program is running on a VM or not. So the reason I'm picking this out is because this often will run. There's an issue with not being able to hear me. Okay. Oops. Sorry, I'm gonna try and see if it says that the microphone's working. Wait. Okay, some people can hear me fine, some people can't hear me. Okay. All right. Apologies. So I don't know what the problem is there. I do know that the WebEx window on my on my desktop here says that it's working fine. So I don't know what would be messing with that. All right, I'll start over. Thank you for letting me know, though, because it's always helpful. It's not clear. Yeah, this thing works different every single day. So anyhow, so I've got a C program here that's very simple. I borrowed it from this Jake and Herman. I made some modifications to it as well to add a few more tests. But basically what it is doing is it basically builds up a score to say whether or not they think that the computer it's running on is running in a VM or not. I actually added a few more checks. What it ends up doing is it basically has a handful of checks. It looks at the number of cores to try and see how many cores are registered to the current processor. One of the reasons for this is, as probably many of you are aware, it's getting less and less easy to find a single core system. Most of them, even if they are a single CPU, they still have multiple threads. However, as most of you have found out, when you are configuring your virtual machines, it's a lot easier from your perspective to only associate one CPU with a virtual machine. Otherwise, you start running into like performance degradation, stuff like that. So the author of this tool uses that consideration to try and help inform, based on that measurement, whether or not it thinks it's running inside of a VM. In addition, another check that can be done is looking at the system manufacturer. So your virtual machine is virtual hardware that may or may not have some sort of, or I should say, it's virtual hardware, so it doesn't actually have a hardware manufacturer. Most computers and everything have a way of like electronically stamping them to indicate who the manufacturer was, whether it was Dell or Asus or someone like that. With virtual systems, a lot of times that stamping is done electronically by the vendor of the virtualization software. So in this case, VMware is, VMware is one of them. So, they do a check for that here. Additionally, there's the registry checks that we talked about, the Windows registry, which is like the configuration library for Windows. Has a bunch of these like key, basically a big hierarchy of these key value pairs that go and define like various configuration settings. A lot of the how should I say, a lot of the system dependent things or a lot of information gathered from the system will also tend to be stored here. So we'll have, say, drivers that go and scan the system, look at the hardware and pick out the different hardware values. They'll write this information in the registry overwriting any old values that were there. So the registry is a good place to go to look for some of that information as well. Yeah. And then also another thing that Windows has, and this is very useful, this is implemented for a lot of times for a developer perspective, is it can be helpful for your program to behave one way when it's running inside of a debugger, and another way for it to run when it's not running inside of a debugger. So for instance, it might be useful for if your program's running inside of a debugger for it to pop up like a debugging window that can give you a lot of introspection into what's going on under the, under the surface of the program, without necessarily being a view that has to be shown to, say, all users of that program. So this is very simple code. The reason I bring this stuff up is mainly to kind of give you an idea of some of the complications that you could face when you're doing any sort of malware analysis, especially behavioral malware analysis. So when you're trying to use dynamic execution to find out what actions or steps is a piece of malware taking. And so we had a few examples, I think the week before I went out of town, where we opened something in Acrobat Reader and we were able to see it writing files to disk and everything like that. We were able to use sysmon to see some of those sequences of steps from that exe program with the crazy like Microsoft Paint icon, and it renamed itself to like two random words that were merged together, .exe, somewhere else in the system. So we were able to see those actions happen, and that was mainly because that malware wasn't ever written to like do VM detection. Sometimes you might run into the case where it is, and if you try and run it inside of your VM, it'll identify it's in the VM, and then you'll be stuck. It'll refuse to perform the behaviors that it was designed to do. So luckily for us, we have a debugger that can monitor the code while it's executing and even allow you to modify the code during execution. So you can see the different values that are being executed and then decide what to do from there. So, yeah.
So if the malware could theoretically monitor for being run inside a VM, couldn't the VM also monitor to check or to see if there are checks being made by a piece of software?
Yes. Yeah. So that the point that was brought up was, couldn't the VM check to see if software is calling certain API calls or maybe performing certain tests? So ideally, yes. I would say that it can be difficult depending upon the sequence of steps that need to be used in order to in order to perform that work. So I'll go ahead and start up this Windows VM that I've been using, because I think I have I think this is the one where I've got the program installed on it. I'll run the program really quickly to show you kind of what its output is in this environment. And then after it starts up, yeah, and then, wait, did I just ask me later? Let me just double check. Yeah, I am doing the right one. Yeah, this is the right one. Let's see. That's going to get annoying, so let me mute it. All right, so this is the program that I wrote really quickly. So that's the program compiled from the source code that's up on the site. I'll just do cmd.exe to get a shell to then run it because how I set it up was rather than popping up message boxes, just have it outputting to the console. So this is it. So basically, I can run it. It manages to look through a number of different basically configuration points or system information buckets to try and get information out. It shows the number of CPUs is 1. It also says virtual machine was detected. It also gives a list of, dumps out some of the information it got out of the registry and so forth. And then it also says not running inside of the debugger. So all of that's interesting. I installed Immunity Debugger on here, which I think I mentioned a few weeks ago in class as a really nice debugger. So some of you might be familiar, especially if you had any co-op courses that involved doing any software analysis or whatever. You might be familiar with using like OllyDebug or something like that. Immunity Debugger is a very similar work-alike to it that is actively maintained, so it's kind of the one I recommend. Mainly just because of I like to use things that are actively maintained by somebody. So if I run it, I'll go ahead and run it. Yep, this one is what I want to. So I'll just put them side by side, right? So what just happened? There we go. Sorry. Oh, whoops. This thing. So you can see that they basically detect the same things. So it does CPU detection, the registry value detection, virtual machine detection. So I believe it's actually using the registry value for the hard disk to find that. And then it also, this new one was positively able to identify that it's running inside of the debugger, right? So that's kind of, there was actually 4 checks here. I'll say that one of the checks actually doesn't recognize this particular VM environment, and I'll get into why here in a second. So when I bring up the source code for it. So, yeah, this is a source code for the program. So we'll jump into the main function here. What it ends up doing is it first calculates the number of cores. I believe there's a global variable here that it's using to track the score, so it basically increments that each time one of these tests pass. And then at the end of the main function, if that score is greater than a threshold value, then it says, hey, I'm probably running inside of a virtual environment. And for the sake of argument right now, we'll say that a debugger also constitutes a virtual environment. So the first one, after the number of cores check is run, and I'm actually going to, this won't be in sequential order. I'll kind of go, I'll just go with where the code is. So, context order here, lexical order. So what's happening here is it actually runs a system info. So system info is a program that exists in Windows that can dump the system information. And I think I can actually run it here if you want to see it. Right? So that's what's doing the sequence of steps, right? Is the system info. This goes through and tells you what all different pieces of hardware and stuff. The idea here is to kind of give you a readout of all of the stuff that's plugged into the system and some of the important system configuration data. So we can go up here and we can see the computer name or host name is there, what version of Windows it's running, what, the detailed version of Windows that it's running, all the OS information, who the current user is, the user's organization if that's registered, the product ID, original install date, system boot time, so when was the last time it was booted, system manufacturer, system model, So in this vein, you can see here that like system model is listed as VirtualBox, which is kind of a very obvious thing to identify. I will say that in the source code I got from the guy's site, that test is actually not looking for VirtualBox. It's looking under system manufacturer for VMware, right? For VMware incorporated to exist. So, it's kind of doing like, oops. I think I can do like that, right? Yeah. So, or I can't remember exactly how find works, but anyway, yeah. Anyway, that is kind of the logic that they're trying to do in order to navigate this. So what they end up doing is they execute one Windows program, right, and that system info, and then that dumps out this entire readout of information. That readout of information is then piped to this find command, and I'm not entirely certain how the test is accomplished here. I guess I can bring that up over here, right? So it does this run command. Yeah, so if I go down here to run command, I can probably see, let's see. So it uses, in this case, it uses the pipe open and everything like that. Basically tries to see if the phrase was detected. So if that VMware, whatever the VMware string ends up matching the output of this, then then it will register a success. So in this case, it says system manufacturer. Maybe I should just look for that, right? Come on, there we go. Find. Right. I don't know. Yeah, so see, it works kind of sort of like grep, right? So if I wanted to, I could basically have a version of it that looked for, what would I call that? System model, right? So for the VirtualBox, this is kind of one of the reasons I didn't implement this particular test for VirtualBox. So basically, I could do that, and the idea is that when I do that, I end up with one line of output. Then that is passed to a loop that then does a string compare between the two things. So to your question earlier about can the VM simply be instrumented to look for cases where the program is trying to do the sequence of steps that would try and do VM detection? The VM theoretically could be instrumented that way. However, in this case, this is a very kind of like arbitrary and complex sequence of steps here. So we're running a system info command, which is extremely common in Windows, and then we're piping it to find system model. And then separate from that, there's an algorithm that was written in C, which is right here in the run command that performs basically this stir does the copy string and then does a string compare. So it does a copy string to bring data from the detection phrase, or basically from the program run output into a buffer, and then it performs a string compare to try and see if that lines up with the phrase that was passed as an argument to this function. So this entire function kind of implements a algorithm that runs the program, looks at the output, and then even adds like null terminator and stuff like that to the output. And then once all of that's done, it let me see, how is this all working? Yeah, once all that's done, it does a comparison to try and figure out if the string that's passed up here actually matches what was output by the program. So writing, or I should say instrumenting the VM to identify this stuff is probably a very potentially complex problem, because while I could probably write something to look for the sequence of commands that led up to this, if a slightly different variation of this algorithm is run, then kind of all bets are off as far as my ability to detect this test, right? So for instance, all the way down to just if the mechanism used for doing the string copy and the string compare was implemented differently, that would basically cause instrumentation to fail there. So there's not really a big kind of, this approach is being used for VM detection. There's not a very obvious amount of information there. And there's all sorts of ways to work around it. So for example, I implemented this with a pipe, which that might be a, just a command string to try and identify. I could easily have implemented this as, output to test.txt, right? I could easily do that, and then open it up as like a file, and then iterate down the lines of the file and look for what I want. Or even just scan the entire file for the words VMware or VirtualBox, which might be a more comprehensive or complete approach. So, from the Defender perspective, it starts to become like a very challenging game for me to try and chase all those things. So that's kind of a complicated one. A simpler one, we'll go up here and look at the is debugger. So is my program running inside of a debugger? We'll look at how that function is implemented. That one's actually a lot more straightforward and might actually fit the bill for kind of that type of solution a little bit better. So here's like the is debugger. So the Win API actually has a couple of functions to do this, but here's one of them. So there's actually a function in Windows that's been in, I don't know how old this is, it might actually say down here. Here you go, minimum supported client. So it's been around since at least Windows XP. So since mid 2000s or something. And basically this function returns true or false, depending on if it happens to be running inside of a debugger. So this is kind of the opposite end of the spectrum, right? This is a much easier to identify behavior. So, and then finally, the other thing that this does is it does the registry check. So what we end up doing is we query the system information in Windows with that run command. We do the debugger check using the is debugger present. We also do a registry check. So we actually go into the Windows registry and look at this. So what I can do is I can actually go over here to regedit just to kind of give a little demo of that. So as I said, the Windows registry ends up being kind of a big library or database of system configuration information. The hardware that's currently connected to the system ends up being incorporated as part of the system configuration. And it'll actually, what's nice about it is that if you were to take your entire Windows installation and then move it over to another piece of hardware, so you remove your hard disk or whatever, and then boot it up, it'll actually go through and query a lot of these things and then compare them to what the drivers currently say is plugged in. And then it will actually end up taking special actions based upon any differences between these. So you might see some of these realized in like, a new device has been plugged in. Please click here in order to install drivers, or please wait while drivers are being installed. Or in the case of like Windows XP and things, you might actually have Windows lock you out because too many hardware devices have changed, and it used to be that Microsoft wanted you to make sure that you had one version of Windows installed per computer, right? So the idea with taking your hard drive, installing Windows on it once, and then replicating that to a bunch of other computers was seen as a potentially easy way to propagate or basically steal Windows licenses. So they implemented some check in there that would basically store the previous hardware configuration when it was last shut down in the registry. And then when you boot it up the next time, it would query all the drivers that came online to find out if there was too much of a delta in the value changes from the previous shutdown state. So the availability of that information gives us the ability to do this. Also, I'll say that its presence works nicely to kind of cache the information, so that if you're using like the Windows device manager, the little tree that has all the hardware devices in it and stuff like that, that can be rendered very quickly to you without having to query every single driver individually. So we'll go to this one, and we'll look at what it looks like in the Windows registry. So I think it was this one. So services disk. Services disk. There we go, and then enum. So what's nice here is, as you can see, disk 0 that's plugged in here is this one. And it has this really, really long value associated with it that includes, like, I think the device version information, manufacturer ID. They come up with a, I think, a unique ordering ID that's based upon how it is physically connected to the system, at least electrically, not necessarily like geographically or anything. But as you can see, one of the other things in here is that it has this value here, VBox hard disk, that positively identifies it as a VirtualBox, like virtualized hard disk, right? So when that code runs, if it's looking for VBox, if it's looking for a VirtualBox to exist, or I should say if it's looking for the word VBox, and that's present in there, then it can get positively identified as a VirtualBox virtual hard disk. So, and that's exactly what I have right here in this function. So this function actually has a list of what I would call hard drive names of strings that are found in some of the common VMs. And so in this case, there's VMware, but then also VBox. What we end up doing here is this value is actually pulled in. If I remember correctly, I don't remember what's doing it, but you saw it happen right here. So if you remember when we looked at that, value, or I'll actually go over here to show you. When we looked at that value in the registry, there was actually upper and lowercase letters, but here when it was extracted, for whatever reason, it's lowercase. Yeah. So that's the reason why I'm safe with doing the lowercase stuff here. Yeah. And that's actually this right here. So, and I missed it, but yeah. So what happens is after we pull it out of the registry, we lowercase all the values, and that way, depending on maybe different versions of VMware or VirtualBox in the future, may opt to have a different capitalization, or individual people might do it too through scripts and whatnot. So what I end up doing here is I have it iterate through this list, So it iterates through that list, and then it basically does a string compare. It looks for one string inside of another string. So this does if a string is identified to be a substring of a larger string, or moreover, if whatever this parameter is inside of this one, then it returns a pointer to the first character. Otherwise, it returns null. So basically, if the result of that's not null, then we increment the VM score. And so the idea here is, you kind of do it for each one of them that are detected. The idea here also is that if, say, VMware and VBox, if different implementations of those maybe had many different hard drive names that were used, I could just have them in this list and it would just like count them all up. So likewise, if there's multiple drives connected and one of them happens to be VirtualBox, but the other one maybe was changed at some point, at least one of them contributes to this. So anyway, that's the algorithm for detecting the presence of a VM using the hard drive controller registry check. So it's kind of doing a little bit of that system forensics that we talked about before too in order to do it. And then finally, there is also number of cores. So how many CPUs is in the system. So this one's really neat because I think like CPU info, right? So you can look at the CPU info here. This thing tells me how many cores the processor on my system has. So in this case, it says that I have 4 cores on the processor in here. And having 2 or more is becoming to be more the norm nowadays. Even if you have like a Core i3 or something like that, many times your laptop will at least have 2 cores. Like anything that's basically based on a Core 2 Duo or newer has 2 cores. Likewise with the AMD chips as well. It's just becoming a lot easier for extracting more like multiprocessing performance out of systems because, to be totally honest, it's a lot easier to, or I should say, it's a lot more heat and power efficient to actually have multiple cores in the system or multiple threads in a CPU than it is to clock the CPU a lot higher. So, and generally speaking, that's what most people are, concerned about is multiprocessing performance, multitasking performance. So it's basically querying that value, and there's a, I did the Linux version there. There's of course a Windows version for doing that too, and that's what's happening here. So basically, we call the get system info function. There's a, this is another API call just like the is debugger present. So again, this is one that is could possibly be a kind of much lighter weight. If you compare it to the registry access, this is a much lighter weight. This is a much lighter weight kind of detection opportunity. So doesn't return a value. It's been around since Windows 2000. So this is a function that's been around for a long time. And basically what it does is it fills this data structure up with a whole bunch of details about the system. So it gives you the page size, some like system address information, processors, processor type, allocation granularity. So how much, what's the minimum quantum of memory that you can kind of allocate into your, into your processor level, processor revision. So, and then it goes and tells you, Windows supports being, or I should say, there are versions of Windows that support being run on all of the platforms that you see here. So this is the old HP Intel chip, the 64-bit thing, and then of course the 2 ARM variants that that exist in some of the embedded and Microsoft Windows Phone environments. So let's see, and then this one is likely what our VM's running in, right? So it goes, all that information is available to be queried. It goes and explains all the parameters here too. So I'm not going to go much further into this, but just suffice to say that it is there. So let me jump back to the code for a moment. So basically, if the number of processors is less than or equal to 1, then increase the VM score. It's more likely that we are running on a virtual machine if the number of processors is 1 or less. And then, of course, that's a global variable that's being used. So kind of that's the entirety of the program. And as I showed you over here, this is, I'll put that in the background. So this is the program running inside of the debugger. So inside the debugger, it identified that both the virtual machine was detected, and also it identified that it's running inside of the debugger. So I'm going to restart this. So one of the nice features of this is that I can go ahead and restart things if I want to. So what you can see is that there are references to some of these strings already in here. So that this is why I worked with like a really simple program. Sometimes you end up having to say load this up in IDA Pro like we had done before, and then use some of identify the strings or something like that, and then try and tie them back or identify function entry points. So for instance, this right here, this right here would be a function entry point. So sometimes you may have to identify those things in order to get an idea of where to go looking. So what you can see here is that let's see, trying to see for 1.70. So I think you can actually probably just do this, right? So I'm up here. I think if I just kind of step down or step, let's see, 41170. Yeah, so what's going to end up happening is it's going to jump down here, which is, I believe, where kind of the main function lives, right? Yeah, so it'll go down here. For that first one, and that's like, or that's not that main function, but just setting it up. So anyway, this is doing a whole bunch of setup. So anyway, I believe that what ends up happening is eventually it gets up here. So there's like your to lower call, and then there's the stir call, so the string comparison call. Here's the found registry value string, so where it outputs what registry value it found, that's there as well. So all the code that is useful to us or interesting to us for doing these various tests is located around here, and I think also the trying to see if the is debugger present call is obvious here or not. But anyway, here it is, and then here's the is debugger present call, right? So anyway, so we can start there with that one. So the idea here is I kind of look for I look for hints, and I might use IDA in order to get me to here, or some other kind of static code analysis tool to help me identify where the memory is located. Or if it's a relatively simple program, I can do what I just did, which is I can kind of scan through the entry code to the program to try and see if I can find the string references just by eyeballing them. So in this case, I managed to isolate that, this function here basically does the debugger test. This function, and this is nice because you can see that this is one of the nice features of Immunity, is it actually allows you to break the functions up like this. So this function right here is the one responsible for the CPU calculation. This function right here is, I would say at the outset looks like it's responsible for checking the system manufacturer, but if you recall, when we were looking at the source code, the main function actually includes that at the top of it. So for whatever reason, this code was put in the top of the main function, which means the rest of this code is code within the main function. And that'll get proved out by looking at these different calls right here. So this one calls a function, then this one calls a function, and this one calls another function, this one calls another function. So they all call different functions that are within the same program. And that's evident because you can see the call to VM detect dot, some local address is here versus this call. So you can see this call is actually different because this call is actually referencing msvcrt.puts. So that's a API or system function, right? Versus this one, which is a local address that's in the same neighborhood as the line that's highlighted. So when I go back here to the source code, should you all scroll all the way back up here to the main function, you can see that basically do the number of cores and then basically like run command, then registry check, and then there's a test for the printfs, and then is debugger. So somehow or another, all that stuff is looped in to the code that I had just highlighted earlier. Let me see. Yeah, and then there's this one right here. So this is probably the is debugger present because, as we saw, that's way at the end of the function. And I can actually test that theory by looking for 4161D, which is just right here, which is this one, which is the is debugger present. So what I can actually do, if I wanted to, take a little bit of time to do it in front of everyone here, is I've identified this as the main function. So then I'd go through here and I would identify this, identify this, identify this. I'd identify this, and then identify, I skipped over it. I would identify this, and I would identify this one, this one, this one, and this one, and I would try and map those to each one of these things down here. So like this one, I can map it here, and then if I analyze this function, look at what it's calling, I can learn that this one's calling the get system info function, talks about the number of CPUs, so that one's responsible for the CPU count. 64B, 74C, so 64B is right here. Look at this, and it is, this one might take me a little bit of more work to try and analyze. I would say that just, I remember looking at the source code, which I have the benefit of having access to the source code in this case, I was able to identify that the only function that calls popen is the one that is the run command function. So this is the run command function that's associated with trying to run this command up here. So, and that's why it happens right there. So anyway, I will, since I know this is the beginning of it, I'm going to put a breakpoint right here. Come on. There we go. Touchy touchpad. I'm going to just insert a breakpoint here, so toggle breakpoint. And then that's going to basically have the program. Now it ran, but it stopped, so it's paused. And that's shown down here. Earlier when I was running it and I ran it to completion, it actually said terminated when I got to the exit. So that's, you can distinguish whether you've managed to pause the program or it's run to the end. I know that in here, this one is, this is the entry to the main function. So if I was to go and try and analyze, every single one of these things, the big thing might just be, this was detecting whether a virtual machine was, was present or not. So this is kind of the calculation against that computed sum. So a very simple approach to this might be if I was to maybe, a good example might be that maybe I set another breakpoint here, and then I let it run until I get here, right? And so now I'm at this stage where it's going to do the comparison between EAX and 2. And it's going to find out that EAX, the variable, is actually greater than 2. Which means that this jump, if greater, is actually going to succeed. I don't want it to do that, so maybe one thing I might do is just try knocking this down to 0 at runtime, just to see what happens. And so I'll step through this using steps. So the difference here in these two, I have these two single step operations here. This one allows me to step down instructions, and if I encounter calls, it will run the function, but it won't step through the function. So it'll stay in the current function, and it will run functions called from this one without following them. This method, if I use this step, called step into, this one will actually jump into the next function when I encounter a function call, and then it will basically try and step through every single instruction there and show me what that's doing. That can sometimes get to be particularly obnoxious, especially when you start stepping through calls to things like where I have the arrow right now.
Is there an output window where you can dump
Yeah.
them?
So the output window's right here, right? So I've run part of the code so far. I've run the part of the code that counted the number of CPUs and the code that analyzed the system info output. And then also I ran the code that did the registry lookup of the hard disk value to try and see if the hard disk model matched VirtualBox or not. And so all those things have been done, and then the value of the, so I'll say that the value of that global variable is actually right here. So that one of the nice things that helps too is you can see that as I'm highlighting different lines, it shows me down in this little window the little kind of hint of what's going on. So that global variable that's in C is actually being tracked in this memory address right here. So 40501C. That one contains the the value 3 right now, and that's shown to me down here. So this instruction, which is the instruction that ran just before the last one that I stepped through, that instruction put that value into EAX. So it moved it from memory into a local variable because it's just a lot easier to do a lot of the local, if you're going to do multiple operations or something like that, it's a lot easier to localize the data. So then after the data was localized, it compared it to 2. But if you remember, right before it compared it to 2, I actually changed the value in the register. So the value in the local variable changed because I modified it, because I paused the CPU. So then, because I had changed the value, and you can see that's still highlighted over here, because I changed that value after it was copied from memory, I didn't have to edit the memory at all. So the program's going to move forward as if basically that test failed. So, and that's what you see here is that even though this is a jump if greater, and that's what the JG stands for, the JG basically says that if EAX was a greater value than the right-hand value of the compare operation, then it would jump to that address, that 5C4, which is right here, right? Otherwise, it's just going to continue executing as normal. And what you can see is you actually get a little bit of a preview of what's about to happen is it's going to say no virtual machine detected. So you can go here, and then here, and then here, and then it jumps to the end of the program. And so then I'm going to show you that this says no virtual machine detected. So this type of technique works in, as long as you can isolate the code and in specifically the test that's happening. So remember, the program itself still performed all the sequence of steps it needed to do in order to test for the virtual machine. The only thing I really did was I just changed the value at runtime of what it was testing against. So I gave it a fake value to test against, but it still did the sequence of steps it needed to do. The other thing that I'll throw in here is that now that I've identified this routine that it's doing here, or I should say this combination of routines that it's doing here, I could hypothetically come up with like a broader example. And this kind of gets to the point that you were bringing up at the beginning of class, which is that there are 4 different algorithms that were in play here to try and aggregate this, is it a VM score, right? I could use some of the static analysis that that we did in the previous homework assignment to come up with a pattern to try and identify, say, this algorithm replicated elsewhere. And then, so say hypothetically that this code sample that I had sits on GitHub, right? Hypothetically, anyone could take a copy of this and then write code around it to basically use it as their kind of test for virtual machine awareness. If I find a way to defeat this, which literally, right now I did it at runtime, right? And I'll actually just let this run to completion. So there, it's run to completion, and then this is what it outputs. So it still knows that it's running inside a debugger, but it says no virtual machine detected. So what I ended up doing was I defeated, or I should say I bypassed it at runtime. What I can do, now that I know how to bypass it at runtime, what I might want to do is go back to that code, and because I knew that what happens here is that either it decides to branch from here if it's a virtual machine, or it stays and moves to the next line of code if it is not a virtual machine, right? So what I might want to do is I might want to modify the code in place here. So another approach I could do so that I could modify this without having to pause the program, so I could bypass it without having to pause the program, is I might want to assemble. So I might actually want to overwrite the bytes that are implementing this test with some other bytes that aren't going to cause the jump to happen. And you have a hint to what those are because it's up top. But basically, I could assemble a no operation there, and then I can overwrite that branch. So it's still going to walk through the sequence of steps to do all the tests. And then at the point where it was going to conditionally jump if the test succeeded, it's actually not going to do anything now. It's just going to do all the tests, and then it's going to throw away the result. So now what I can do, and I'll just go past these points. So now you can see that now I have made a change that was really a 2-byte modification to the code in order to tell it to bypass that virtual machine detection. So, oh, I have to do this. So let me restart it. What I might want to do, whoops, is so XXD is a very neat tool. That allows me to actually see the hex dump here, right? So I can see the hex dump of the entire program. So how about if I try and see if I can isolate, I'm going to actually turn off these breakpoints too. Did that get it? Okay. Okay, cool. So I'm going to try and isolate the code that's contributing to, you know, to this right here. So is this right here. So maybe it says 83F802. Now I have to remember, I think it's, I can't remember exactly. I don't know. Yeah, that's not it. Actually have to go back up here, 45A. So yeah, so this is going to be in sequence, right? So what I can do, oh whoops. What I can do is, right? This is where you end up using a combination of some of the binary operations in Yara to try and identify the code sequences. So let me look for 83F802.7F-OE, right? Oops. What did I say? 7F-OE. And so that might be unique enough. We can find out. Okay. Let's see. Happens one time in the file. So that's really helpful. Because that like narrows down the code to what I want to narrow it down to. So it says it's at position 9B1, which is going to directly map to the addresses that are in here. So let's look for 9B0. And then we can see that the code that we're looking for is actually right here, right? So what I might want to do is look for the comparison, which is represented by 83F802. So that comparison's there, and then the jump if greater than is 7F-OE, so it's 2 bytes. So what I might want to do is just replace it. And so this is, you can do this with a GUI hex editor. I've been using this tool for quite some time, so I'm still using this tool. But what this tool ends up allowing you to do is it allows you to output a textual representation of the binary data. And then I'm going to be able to use the tool again to reconstruct a binary file from what I just did. So I just need to make sure that I do this. So basically, let me see if I can remember reverse operation. So you do it in reverse. And so what I'm going to do is I'm going to give it the modified file tech2.exe, right? And then just to test it, you can see that I don't match on the 2.exe, but I do match on the one of them. And let's try this. So for those of you who aren't familiar, SSDeep is a blockwise hashing tool, so it computes a sequence of blockwise hashes. So the idea is that allows you to capture similarities between files in a kind of hash format almost, in a way so that small changes to the file will result in small changes to the file hash. And so in this case, what I ended up doing was I ran it with just that change, and you can see the two are similar except for the first block. And then this tells you how big the block size is. So the first block was changed. So now what I'm going to do is I'm going to take that vmdetect2.exe and I'm going to put it in the VM exchange, which is my kind of drop folder for everything. So, and then, whoops. So then you can see the VM detect is right here. There we go. So now is right here. So let's run the VM detect just to, so that we have the output right here. And then I'll do vmdetect2.exe. And so you can see the difference right here. Virtual machine detected, no virtual machine detected. So the nice thing that I've done here is that I was able to take the program that I'd hand analyzed and I ran it to try and tinker with ways to bypass the VM detection routine, this particular one. And then I wrote a Yara signature based on the binary data to try and look for the presence of that. Using the Yara signature, I was able to pinpoint the location in the file, not necessarily in memory, but in the file. So I'll answer your question in a moment. If I wanted to add, if I want to then use the positions that are reported to me from the file, which may not necessarily line up to memory positions that the debugger is seeing, I can take that information from Yara. So what I'm talking about is this value right here. And then I know where to perform my patches because I wrote this detection in the first place. So this detection, I knew that the last 2 bytes of it are the ones that need to be overwritten with the byte value 90, right? So, and then I manually did that using XXD. So I, converted it to a hex editor, etc. I could hypothetically write a Python script to work all those steps into one kind of tool, which then, if I have a way to predictably identify this mechanism for doing VM detection, I can have a Python script that I can run all my programs through to figure out which ones match this particular VM detection routine and thus need to be patched before I send them on to like an automated sandbox or something like that. So, what I did first when I ran through this was a sequence of steps that involved me pausing the program at the point where a certain test was being made. And then I had to go and change the CPU register in order to get that test to fail. That's a very nice, unintrusive way of doing the job, but doesn't scale very well. After I figured out how to do that, I came up with a different way, which was actually overwrite some of the bytes in the file with no-op bytes, basically, to have it so that when the program ran from beginning to end, it actually bypassed the check altogether and gave me the output, at least for that particular stage, that I wanted to see, which told me that no virtual machine was detected. So if this was malware, then hypothetically, after that, test fails there or succeeds, depending on what you want to call it, it would then fall into the code that would start trying to connect out to the network and do all the malicious tasks and everything, right? The nice thing about this mechanism is I've come up with a systematic way to be able to edit the file so that I can take all my programs and I can send them to an automated sandbox if I want to. So all these programs that would have been failing in the automated sandbox because they would have been positively identifying VirtualBox now have a way, at least if they're using my algorithm, now I have a way of translating them into a file that will work in my VirtualBox and therefore allow me to better scale my analysis efforts across my data set instead of having to push all these aside and hand analyze them. So in the real world, what you'll end up with, especially if you end up doing kind of research that's focused on maybe one particular tool set or maybe one particular adversary or something like that, you'll start to identify cases where like code reuse is very common, and you'll start to identify the patterns that can, that can lead to, the patterns that can lead to the, detection. So in this case, what was neat is that this is actually a pretty simple and relatively position independent piece of code. I will say that, and some of you might have already picked it out already, one key component here that is kind of difficult is that this presupposes that I guess that would be 14 bytes, or 14 bytes I think, or 15 bytes. I don't remember. Basically presupposes 16 bytes. That's it, because this address right here, the one that I have the arrow on, which is OE, that's 14, but it's always 14 plus the next instruction. So since this instruction is 2 bytes long, it's actually going to be 16 bytes past the beginning of this instruction. But there's basically a hard-coded address in there that says that the destination for this jump needs to be 16 bytes past this, or 14 bytes past the next instruction, which means that if any code, if say the author came and modified this a bit, and maybe, so you can see this thing is calling put s, if it also called something else, then it might increase the address distance between the two. And thus, what I'm trying to match on with the Yara rule here, whoops, and thus what I'm trying to match on right here might end up not being precise anymore. Because if you add code between the test and then where the destination is going to be, the destination is going to slide and it's no longer going to be a difference of 14. It's going to be a difference of maybe 20 or something like that. So this is where it comes in handy to maybe write code that ignores those details. So we can see if, and so at least in this case, that still ends up matching on one of them, and I still know that I can overwrite the data at the end if I want to. So there was a question from someone about what happens if you want to add bytes to the file where none were. So I take that to mean if I was opening this up and I decided that, let's see if I can find where I made that patch. I think it was like 9B1, I think. So it's this one right here. So what happened if I wanted to like insert extra data here? Well, you run into the same exact problem that I was talking about earlier, which is that all of this code, after it's been compiled and linked together, has a large number of positional dependencies. So this code here really only works, this jump really only works as long as this right here, oh, whoops, Windows is shutting down because of the whole VM thing, but it's the end of class. So after the program is compiled and linked, very often you end up having positional dependencies all over the place, which is certain strings always have to be located within a certain relative distance from other things. Certain functions are going to be kind of relatively referenced. So if you start inserting bytes, you end up moving the physical location of those pieces of code, of those blocks, to other places within the file. And then they'll no longer line up with the code. So for instance, if I was to add 1 byte in here, so if I was to insert 1 byte in here, because the strings actually occur toward the end of the file, every single string that printf references is now going to be offset by 1, and I don't have any way of going back into the program and then adjusting all those very easily. I have to manually do that. So the short answer is don't insert or remove any bytes when you're trying to edit a program unless you really want the program to fail. So it's generally not designed for inserting or adding bytes. If you do want to do that, there are some kind of more complicated ways to add functionality without moving things around. But as a general rule, when you're working with exe files and stuff like this, there's so many positional dependencies that you do not want to shift position of any data in the file. You only want to replace bytes with other bytes. So anyway, it's the end of class, and Windows is shut down on me because of the activation thing. So I'll go ahead and let it go for today, and we'll pick up on Thursday.